Hello, Organic Chemistry 2330. We're going to continue on with Chapter 11 and continue with IR spectroscopy. As I ended the last one on, we have these four regions of the IR spectrum to work on. Okay, so in our four bands, we have our light atom, heavy atom bonds right here, which is going to be on our higher end above 2500. We have our triple bonds between 2000 and 2500. We have our double bonds between 1500 and 2000, and we have our single bonds from 1500 to 400. So what we're going to do is we're going to expand upon that and look at the different functional groups that fall within those different regions. So different functional groups absorb in different ways, and based on the polarity of the bond, it tells you whether they're going to be a strong, medium, or weak intensity. Okay, so let's look at that as a function of the alkanes first. Okay, so if we have a carbon-hydrogen bond, it has a stretching bond, and because of the stretching creates a polarity of the bond, we actually end up starting with a strong intensity here. If we look at the bending modes on these, those become weaker and weaker and shift lower and lower in energy. Okay, so if we look at alkenes, because we have a carbon-carbon double bond, we're in that range between 1500 and 2500. And so we're seeing that that's where it comes up. But because that's a nonpolar bond, it tends to be weak to medium, okay? Because remember, the carbon-carbon has the same electronegativity, so it has a weak stretch, but the vibration will show up in that region. Now, the hydrogen bond to an alkene is still going to show up in that upper band because it's the heavy atom, small atom that has a higher energy vibration, but it also is going to also be weak. Once we get to the alkynes, the triple bond is found in that 2000 to 2500 range, and this alkyne hydrogen is also shown in that high end between 2500 and 4000. Okay, so what would a common spectrum of an alkane look like? So the only things we have going for us in that is a carbon-carbon single bond and a carbon-hydrogen single bond. So we should see it in 2 to 3 different ranges, okay? So if we look at here, this is going to be our range where we're going to see our carbon-hydrogen stretch and bond, and then we're going to see our carbon-carbon bond, and then we have some stuff in our lower energy range. This stuff in the low energy range tends to be a carbon-carbon or carbon-hydrogen wag or wiggle. So we see our two stretching frequencies between the carbon-carbon single bond and the carbon-hydrogen single bond found as being the more intense peaks that we have. Okay. So in contrast, if we add that carbon-carbon double bond to it, we gain a peak above this 1500 right here. Here's our 1500 to 2500 range is right here somewhere. And so we gain this peak that we didn't have in the hydrocarbon. We still have our carbon-hydrogen peak for an aliphatic stretch, but we gain a small peak here for our carbon-hydrogen on a carbon-carbon double bond. So now that we have different types of frequencies between the different carbon-carbon single bonds, we start seeing more and more of these peaks come in, and that's different bending and stretching modes. But the key ones that we're looking for is the fact that we now have a new peak in this range, and we still have our carbon-hydrogen peaks up in the carbon-hydrogen peak range. Okay, now if we move to an alkyne, what we see is, again, our new peak in the carbon-carbon triple bond range. We don't have the peak where the alkene was. We still have our carbon-carbon single bonds. We still have our carbon-hydrogen stretches and wags. And we have our carbon-hydrogen bond for the main chain right here. But then we also have that terminal alkyne that's separated out because the carbon with the triple bond on it has a different polarization. It makes this bond a little bit higher, and we can separate it out from the other carbon-hydrogen bonds. Okay, so we can actually follow with IR going from an alkane to an alkene to an alkyne, seeing those bonds shift as they go. So this is one of the big things that IR is helpful for, is looking at functional group transformation. So let's go look at another functional group, okay? So the next functional group I want to talk about is alcohols. And so here we have something that is different from before. We have an OH stretch, okay? Now OH, that's a very polar bond, and it's prone to hydrogen bonding, which means it makes a big, wide, huge peak. It's highly absorbing because of the polarized bond, but then it also can bond in a bunch of different ways through hydrogen bonding, so the peak gets big and broad. We still have the peaks we saw before with our carbon-hydrogen bonds, and we still have our carbon-carbon bonds here, but we add a new peak in our carbon-oxygen section here. So this is the carbon-oxygen stretch, and then we have some other peaks that are showing up in the fingerprint region. Okay, so that's how we can identify alcohols, is that big, broad peak in the high end of the scale. So if we take that alcohol and convert it into an ether, we no longer have that OH right here, which means our peak goes away here. We still have our carbon-hydrogen stretches, and we still have our carbon-oxygen stretch. And these are our carbon-carbon stretches as well. But if we took like ethyl alcohol and converted it to ethyl ether, we would lose that OH peak in this region. So we can actually look for that functional group transformation. Okay, so amines, we have a couple different things to play with here. The fact that our amines can be of a couple different kinds. If we have a primary amine, that means that we have two hydrogens that will show up in that nitrogen-hydrogen range in the high end. So we'll have two absorptions in that high band here. If we have a secondary amine, that means we have one hydrogen that'll show up in this region here, this upper region here. And if we have a tertiary, there are no hydrogen in that range. We will only have the carbon-nitrogen bonds that show up down in this range here. Notice we still have the carbon-hydrogen peaks that show up. Anytime we have an alkane, those carbon-hydrogen peaks will show up in this region. Okay. So if this is a primary amine because it has two peaks here, if we were to functionalize it, one of these peaks would go away. And if we were to make it into the tertiary, both of those peaks would go away. Oh. Both of those peaks would go away. All right, so now we can move on to another functional group, which is aldehydes and ketones. The distinct thing about the aldehydes and ketones is we have a carbon-oxygen double bond. And so as such, we have a big, huge peak in our carbon-oxygen double bond range and our carbon-carbon or carbon-oxygen or carbon-nitrogen double bond range. We still have our alkane type peaks over here. So we have our carbon-hydrogen, and then we have some carbon-carbon, carbon-oxygen, et cetera, peaks in this area here. But the big key here is that we have a big peak between 1500 and 2500, and it's the carbon-oxygen stretching frequency. Okay. Now, when we move to a carboxylic acid, we again still have that CO stretch. We have that big song double bond here, but we also have the OH on the end here. That OH on the end is this big peak we show here. It's overlapping our carbon-hydrogen bonds that would be here. So we see a combination of three different peaks. We have our strong C double bond O peak, we have a strong OH peak, and then on top of that, we have our carbon-hydrogen bonds. Okay, this is very distinctive for carboxylic acids to have both that carbonyl peak and that OH peak. Usually you can tell the difference between a ketone and an alcohol because one will have a peak in one way and one will have the other. This is the combination where we actually have both of those peaks in the same spectrum. Okay, so if we take that carboxylic acid and convert it to an ester, that means we lose that OH functionality here. We take the OH away and we turn it into a carbon-oxygen bond. And so what we see is this peak goes away. We still have our carbon-hydrogen bond here, but we still have our carbon-carbon double bond, and then we have COs and CC bonds in this range here. So we can actually see a conversion from our carboxylic acid to our ester by watching the peak in this band go away. Okay, so amides are similar to the amines. In the case of an amide, we have a C double bond O to a nitrogen. If that nitrogen has hydrogens on it, we'll see peaks in this range here. If we have a primary amide, we'll have 2 peaks. If we have a secondary amide, we'll have 1 peak. And if we have, like in this case here, we have both of those hydrogens knocked off of that nitrogen, we'll have no peaks at all in this range. All of the CHs here show up in our CH band here, and our carbonyl shows up in our carbonyl section between 1500 and 2500 wave numbers. Okay, so again, if this was not fully functionalized, if we had hydrogens on these nitrogens, they would still show up in this range. Okay, so here's an example of a secondary where we do have a hydrogen on here, and that gives us a single peak up in this nitrogen-hydrogen range. We still have our carbon-carbon carbon-hydrogen bonds. We have our carbon-oxygen bond, and then these are our carbon-carbon bonds as well. Okay, so now that we have a primary amide here, we have 2 hydrogens on our nitrogen here. So we see 2 peaks in our nitrogen-hydrogen section. We still see our carbon-hydrogen bonds, and we see our carbon-oxygen double bond in that region. And then, of course, some carbon-carbon bonds as well. So now we've gone through IR spectroscopy and look at functional group transformation by watching peaks grow in and peaks leave as we convert from one functional group to the next.